All right, Anna, can you hear me? If you can, type yes. And while you're doing that, I pulled up the test. It's going to be kind of hard to see, possibly. But number 2 talks about which statement is true, and then has a bunch of things dealing with Avogadro's number and molar mass. And then number 3, the mass of one molecule of C2H2. Are those the 2 questions that you're asking about? Okay, I'm going to try and zoom out. Let me know if that you cannot read that. All right. So Anna, and for everybody else, number 2, which statement is true? Okay. The answer is A. So let's look at everything else and talk about why it's not true. B, 1 mole of mercury atoms is 6.02 times 10 to the 23rd grams. Okay. 1 mole is this number, 6.02 times 10 to the 23rd, but 1 mole is not that many grams, it's just that many things. If a mercury atom weighed 1 gram, which would be crazy because a gram is a decent amount of matter to be 1 atom, then this would be true. But 1 mole of mercury atoms is not 6.02 times 10 to the 23rd grams. C says 6.02 times 10 to the 23rd atoms of mercury is 200.59 AMU. That is not true. If it said grams, that would be true, but it's AMU. Okay, the mass of 1 mercury atom is 200.59 AMU. But a mole, or Avogadro's number, or 6.02 times 10 to the 23rd atoms, is going to be 200.59 grams. Okay, let's go over to the other ones. D says the mass of 1 mercury atom is 200.59 grams. We just talked about that. That's 200.59 AMU. And the molar mass of mercury is 200.59 grams per mole. That part is true, but the first part is not. All of these statements are false, and that is not correct, because if we look back at A, I get this paper straightened out. A says the mass of 1 atom of mercury in grams is 1 over Avogadro's number of the molar mass of mercury. Okay, so 1 602 times 10 to the 23rd, whatever, of the molar mass, which would be 200.59 grams. So essentially, you're just taking the molar mass and you're dividing it by how many things make that up, and that gives you the mass of each one thing. Angela says, what's the difference between AMU and grams? AMU is atomic mass units. It is the unit that we use to measure the mass of an atom, an atomic mass unit. So it's a very, very small amount of matter, amount of mass. A gram is something that we actually use in real world, in real life. The SI unit for mass is kilogram, and that's because we more readily use kilograms. But the gram is, when you go back in lab and you weigh something on a scale, you're getting a reading in grams. Okay, so that's a unit that we're going to use, and we related Avogadro's number and molar mass and AMU. We related those all to each other so that it would be the same number. Okay, so the molar mass, if you find that number on the periodic table for any element, that number is the molar mass of that element. Okay, the mass of a mole in grams. How many grams is 6.02 times 10 to the 23rd of those particles of that element? And then it also means the same number is that many atomic mass units, or AMUs, for one atom of that element. Okay. So AMU is talking individual atoms. Grams is for talking about lots of atoms, close to, around a mole. Okay. Bonnie, the Schussler, that's me. The final is hard if you don't know what you're doing. If you know what you're doing, then it shouldn't be too bad. Is hybridization, let me do a quick run through and hopefully be able to tell if it is or not. Hopefully I don't accidentally skip over it. No, it should not be on your final. Heinrich says, on the practice final, number 2 asks about which number is most precise. How do you figure that out? Let me look that up so I can see what we're talking about, because we kind of talk about precision in a couple different ways. Fonnie, I'll get to yours next. And then, Angela, did you have a question earlier about something? How do you solve the last problem on the test? Number of atoms of oxygen in 5.72 moles of iron 3 nitrate. Yeah, I can go over that too. So Heinrich. Practice final number 2. All right, so practice final number 2, the correct value for, wait, no, that one. Is that the one you're talking about, Heinrich? The correct value for the length of a metal rod is 22.6 centimeters. Which of the following sets of measurements of this rod could be considered precise but not accurate? Type yeah. Okay, good. All right, so I can't show you guys this because it's on my computer, but it's number 2 on the practice final. It says the correct value for the length of a metal rod is 22.6 centimeters. So that is your accepted value. It's the correct value, okay, 22.6 centimeters. Which of the following sets of measurements of this rod could be considered precise but not accurate? Okay, so precision in this regard is having multiple trials or calculations give you the same results. Okay, so having numbers that are essentially just close to each other, but not accurate. So they want them precise but not accurate. Accuracy is hitting your target, is hitting your accepted value, getting close to that specific spot, that specific value. So if we have data that is precise but not accurate, the multiple trials are close to each other, but not close to the accepted value. So in this question, accepted value is 22.6. Okay, A says 22.5, 22.7, 22.6. Those are right around 22.6. One of them's directly on it, and they're all close to each other. So those are going to be precise and accurate. B says 12.6, 22.6, 32.6. Those are kind of all over the place. One of them is accurate. The other two are, one's 10 more, one's 10 less, so those aren't close. C says 20.4, 20.2, 20.5. That looks like that could potentially be the right answer because those are all pretty close to each other, but they are not necessarily very close to 22.6. And then D says 24.6, 23.7, 25.9. So C is going to be the best answer there because those are the closest to each other, 20.4, 20.2, 20.5. But the accepted value is 22.6, which they're about 2 or more off from. So we could say those weren't really accurate, but since they're all close to each other, they're precise. Okay, so answer number 2 should be C. Fani, all the questions should be mixed up. Okay. So back to, I think Angela's question was next. I'm going to scroll up to that. Is how do I solve the last problem on the test? That was the number of atoms of oxygen in 5.72 moles of FeNO33. So let's look at that. Okay, so this was on your guys' Unit 5 test. Oops, I just knocked the thing around. Okay, so we have, let's say, 5.72 moles of iron 3 nitrate. Okay, so FeNO3. Okay, so that would be iron 3 nitrate. You don't really need to know that for this problem, but hopefully you do know that. And we want to know how many atoms of oxygen there are. Okay, so we want to know atoms of oxygen are in that many moles, which again, a mole is just a number. Okay, so how many things we have, how many of these we have, if we have 5.72 moles of them, would be 5.72 times Avogadro's number. That's how many of those we'd have. All right, so well, we want atoms, and we have an ionic compound. We have the formula here, ionic formula. We got our metal, we got our polyatomic ion, negative, non-metal essentially. So if we have this many moles, that is how many of these whole things we have, which each one of these has 3 times 3, 9 oxygens. Okay, so for every one formula unit, if I was just looking at one formula unit, okay, kind of like saying one molecule, but not technically a molecule because it's an ionic compound. So if we just had one of these, that'd be one iron, that would be 3 nitrogens, and it'd be 3 times 3, 9 oxygens. Okay. So we have 5.72 moles of this. Okay, so we have to turn those moles into how many particles. In this instance, we're talking formula units. Okay, so I have to do a moles to particles conversion. Okay, so I have 5.72 moles. Sorry if you guys can't kind of see exactly. Actually, if I move this down, that might be better. Okay, so we got to do conversion here. We got to go from moles, and we want formula units. They want formula units. So I'm going from moles to particles. And then in this specific example, we're calculating formula units, okay? Not molecules, not atoms, formula units, okay? So we got to go with moles, formula units, so we got to get moles to cancel out. And we know that in 1 mole is 6.02 times 10 to the 23rd formula units, okay? So by doing that conversion, I'm going to get how many formula units, okay, how many of these whole things that we have, okay? So Avogadro's number times 5.72. So we should have around 3.44, and I'll just cut it off there, times 10 to the 24th formula units. Okay. So if I wanted how many of these do we have, that would be it. But this problem says atoms of oxygen. It wants how many individual atoms of oxygen we have. So we have, I'm going to move this over. We have, from that above problem, 3.44 times 10 to the 24th formula units. Okay. And in each formula unit, okay, for every 1 formula unit, there are 9 oxygen atoms. Okay, so I'm going to multiply however many formula units I have by 9, and that should give me how many oxygen atoms there are. So you should get somewhere around, like, I'm going to round a little bit more, like 3.1 times 10 to the 25th atoms. Jesse, we haven't learned that yet, so don't worry about that. Okay, so Angela, let me know if that is good or if you need more clarification. Bonnie, do you have a specific question over dipoles and polarization that you want me to talk about? Jesse, yours is by section. So it starts from unit 1, labeled unit 1, you have all your unit 1 questions, and then it goes to unit 2, and then all unit 2 questions. Okay, so Fani says, how do dipoles relate to polarity again? Okay, so let's look at a couple molecules. Let's look at let's look at CO2. Now, if I want to tell if this whole thing is polar, if carbon dioxide is polar or nonpolar, okay, you got to consider for polarity of a molecule, you have to consider, are the bonds polar or not? Are there any polar bonds or not? And you have to consider the geometry / the symmetry. Okay, if you can have instances of both, where you can have 4 instances essentially. You can have something that has nonpolar bonds and is nonpolar, or nonpolar bonds and polar, okay, based off symmetry. Or you can have something that has polar bonds where they all cancel each other out because of symmetry and therefore is nonpolar, or has polar bonds and is also polar. Okay, so there's pretty much 4 outcomes that you could have. So for instance, CO2's best structure looks like that. Okay? Let's first draw each of these bonds as a dipole to show if they are themselves polar or not. Okay, so if I was going to do that, I would take the difference of electronegativity for carbon and oxygen. These are both carbon to oxygen bonds, so they're both going to be the same. Oxygen should be 3.5. Oxygen is 3.5, which is going to be the higher one, and carbon should be 2. Oops, that should be a minus sign. And carbon should be 2.5. Okay, so the difference in electronegativity here is 1. Okay, that fitting into the polar covalent category. Okay, so those are polar bonds. So we can draw that two ways. So we can do an arrow pointing towards the negative with the positive on one side, okay, or we can do the small Greek letter delta with the different signs for the different poles, positives and negatives. So CO2 has polar bonds, okay, because the difference of electronegativity is 0.5 or more. But because of symmetry, because these are pulling in complete opposite directions to the same degree, having both of these oxygen, both having the same electronegativity, this molecule is non-polar. Right? You need to go, if this is something that that's confusing, you want to go back and look at bond polarity practice, molecular polarity practice, and use the notes, look at that polarity flowchart. So to determine if CO2 is polar or non-polar overall, I would go to the molecular polarity flowchart, and I'd say, okay, this molecule is linear. So then you're going down the left side. So then after identifying the geometry linear, you have to say, does it have any polar bonds, or are they all non-polar? If those were non-polar bonds, this would automatically be a non-polar molecule because it's automatically going to be symmetrical in terms of all of the bonds being spread out as far as possible. But having nonpolar bonds is not going to affect that difference in polarity or electron density at all. Okay, so this having polar bonds, we're going to go a little bit to the right, kind of stems to the right a little bit, and then you have to look at symmetry. You have to look at essentially what are the outer elements. If they're the same, then this is symmetrical, okay? Which means both dipoles cancel each other out, which means this is nonpolar overall. Okay, so CO2 would be nonpolar. If, for instance, one of those was a sulfur, it would be polar. Okay, so if I changed one of these outer ones, if I put anything there besides oxygen, it's not symmetrical anymore, because if I cut it down the middle, oh, you know, I got sulfur or whatever over here, and I got oxygen over there. Okay, it's not the same. Here, they're both oxygen, so it's going to be nonpolar. Okay, nonpolar is 4.0 or less, or sorry, 0.4 or less. 0.5 or more is polar. And then ionic is going to be 2 or more, or if you have a metal and a non-metal. So these are all non-metals. If you have a metal, it's automatically going to be an ionic bond, because that ionic bonds are between metals and non-metals, positives and negatives. Okay, there are some exceptions to that, like beryllium. We know is technically a metal, but it makes covalent bonds. That's one of those exceptions that you need to know that only makes 2 bonds. But if you want me to do another problem, fine, I can, but I would check out the notes. If the electronegativity is 1, how is it nonpolar? Because they cancel each other out. I wish I could show you the notes. It's in the flow chart in the back of molecular bonding notes. We would first, I'll kind of draw it out. I'll try. First thing you look at is geometry. Where it goes to the left, it's going to be linear. This is a linear molecule. It's AB2. And then from there, you have to look at are bonds polar, or sorry, are they polar or are they all nonpolar? In this instance, there is at least one polar bond. Okay, was a one or more, at least one. And then after you go to polar bond, then you have to consider, okay, is it symmetrical or not? And then you would go this way, it is symmetrical. Which is going to point to nonpolar. Okay, but like I said, if so if this was like a sulfur, that would make this not symmetrical. So then you would go this way where it says asymmetrical, and that would take you to polar, okay, where they wouldn't equally cancel each other out. All right, let me know if I'm skipping everyone, because I kind of forget if I haven't done everything. So I got Emma. Can you go over 64 on the practice test? All right, so let me pull that up. So this is for chemistry, regular chemistry. So Emma, hopefully you're listening, just to make sure I have the right number 64, because I might have slightly changed something around and it could have messed up numbers. But are you talking about what is the formula for sodium carbonate? Say yes if it is. Yes, Fani, I think you can do well. If you know what you're doing and if you've been paying attention and you've practiced. Ammonium nitrate. Okay, so that's my number 63. I think if you go download it now, it's number 63. Okay, so let's do that. Let me get rid of this quick. So what is the formula for ammonium nitrate? All right, I gotta remember that because I gotta go look at this thing. Move this over. Go back down here. All right, formula for ammonium nitrate. Okay. So this is an ionic compound because there are no prefixes. There's no, mono, di, tri, tetra, anything on any of these. Okay, so it's definitely a metal and a non-metal. Another giveaway is this ends in 8, okay, which means polyatomic ion, which means it has a charge. So we have our negative here and our positive here. So I have to identify what both of these things are. Okay, ammonium is our metal. And if you spend time looking on your periodic table for ammonium, you won't find it on the front. That's because it is the only positive polyatomic ion that I'll ask about. There's another one called hydronium, which might be on some like homework questions, but it won't be on your final or a test because you don't see it very much. So if you look on your periodic table, top left, okay, polyatomic cations, ammonium and hydronium are the only ones. Ammonium is NH4+. Okay, you might not be able to see that, but you have your own periodic table, so you can figure that out. Okay, so I have and then nitrate, okay, is, well, where would we find that? Okay, so it's nitrate, okay, which is going to be nitrogen, but with other elements. It's a polyatomic ion. It's multiple atoms, multiple atom ion. Okay, it has a charge. So if we go back to polyatomic ions, everything else here are the negative ones. This one's with nitrogen. So that's going to be a group 5 element. Okay. So if we scroll down, we see like arsenate, something called azide, which is kind of weird. Oh, here's nitrate. Next to it is nitrite. Don't get those confused. Okay, and nitrate is NO3, and that whole thing is a -1. Okay, so NO3, and that whole thing is a -1. Okay, it's not 3 negative, it's NO3 and a -1. Okay, the whole thing is -1. So when I put these two things together, when I put ammonium with nitrate to make ammonium nitrate, I have to balance their charges. I have to neutralize it. I have to get the charge to 0 overall. Okay. So ammoniums are all +1. Nitrates are all -1. So if I have one of each, is it balanced? Yes. The charges will go away and it will balance out. So when I put these two together, I just need one of each. So I literally just write them next to each other. NH4, but I don't put that positive here because it's gone away. A +1 thing with a -1 thing is going to make it overall charge of 0. Okay, it's going to go away. And then I write nitrate just right next to it, NO3. I don't put a negative here because it went away. This is a positive thing, that's a negative thing. Put one of each together. There are no more charges anymore. Okay, they canceled out. So your formula should be NH4NO3. And that was number 60, my 63, maybe 64 on the regular chemistry practice test. Okay. Jesse, no, there is no writing portion. Okay. Daniel says, could you do the Lewis structure for a polyatomic ion? Daniel, is there any one ion that you have in mind? Oh, and sorry, Heinrich, I just saw yours. I'll get to it after this question. Okay. Okay, so Daniel, nothing specific. Let's do, let me see if I can think of a hard one. I'm going to do some investigating on the final. All right, I was going to make one up. Let's do a good one would be SO. Oh no, that's but not part of my kind. Let's do, I don't know, SO 4 2 minus. Let's do sulfate. Okay, so if you look up on the back of your periodic table, SO4 2 minus, that's sulfate. Okay, so Lewis structure. We need some room. Let's count up electrons first. So, oops, can you guys see that? Nope. Sulfur has 6. There's one of them. Oxygen has 6. There's 4 of them. Okay, so we're going to add those together. And it is a 2 negative, so we're going to end up having 2 extra electrons that we got, and it doesn't really matter where they came from or what, but this is a polyatomic ion. It needed 2 extra electrons, so they took it from somewhere, from some other elements, and it gave it that charge, okay, and that made it stable. Okay, so we have in all 32 valence electrons that we have to add to this structure, okay? So starting Lewis structure, you put the center atom first. That'd be sulfur because it's first. And we're going to single bond it to all 4 other oxygens. Okay, so we'll start there. 2, 4, 6, 8 electrons we've used so far. We got to get to 32. So we're going to start going around the outer ones and start putting on more electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. It works out great where everything right now has 8 electrons. Okay. Now, Emma and Jesse, if you're watching this, I would not give you this question because you would actually stop right there. My advanced people, you would look at formal charges and you would say, oh, oxygens all around are going to have -1 charges. Okay, and sulfur in the middle right now is a +2. If you need me to go over formal charges, I can do that. But remember, it is the valence electrons that it has normally for that element minus the formal electrons, which you count a bond as 1 electron, and any lone pairs would be 2. Okay, and that's because, you know, if like sulfur and oxygen are sharing those 2 electrons, so we're just going to say each of them has 1 formal electron. They formally only get 1 at any given time. Okay, so these are our formal charges here. Lots of formal charges. This one goes up to 2. That's pretty high. The best we could do here, if the overall charge of this polyatomic ion is 2 negative, -2, the best we could do is just have 2 -1s on that molecule. Okay, and we can actually do that here by expanding sulfur's octet. Sulfur expands its octet a lot, especially with sulfur, sulfate, sulfite. So what we're going to actually do here is take maybe those 2 electrons and we're going to put them in a bond. Okay, so we're going to double bond. We're going to expand sulfur's octet. Now it has technically 10 valence electrons. Okay, and by sharing that there, that formal charge on oxygen is going to go away. And this would actually go to +1. And if we do that again, let's take, say, those 2 and instead share those. Okay, so, you know, I'll just cross those out, I guess, cross those out. Okay, that's going to make that -1 go away. And then this was +1 after there we shared. If we share again, that's going to go away too. So now we're just left with 2 -1s, which is the best you're going to get because overall this is 2 negative. So you have to have at least 2 -1 formal charges. Okay, and then this polyatomic ion, okay, to show that it has a charge, we put it in brackets, and we put that charge up in the top right. Okay, so that would be our best structure, and then even a little bit farther in terms of resonance, we could actually get, I want to say, 6 structures of this, okay, which I'm not going to draw because that would take a lot of time. But we have 2 double bonds and 2 single bonds. We could have the doubles there. We could have them there. We could have 1 on top, 1 on bottom, 1 on left, 1 on right, 2 of them there, 2 of them there. So you could essentially have 6 different structures for this. So if I really asked that on a test, you would potentially have to draw all of them, and then you would include those arrows saying that really, like, this structure on its own is not perfect. It's not a double and a single. it's really like they're all 1.5s. So that would be how to draw a pretty complex polyatomic ion. Daniel. Jason, I'm seeing you've been asking a lot of questions. The overall charge on the polyatomic ion is either told to you, you look on the back of your periodic table and you just find it and it tells you the charge, okay? And if you're looking at formal charges, if you're trying to figure out which structure is best, you want to minimize your formal charges, but like in this instance, I'm going to have 2 -1 charges, okay, at the very least, because I gained 2 electrons. So some atom somewhere, one of them or 2 of them, in this instance, having gained 2 electrons, there's going to be an extra formal electron hanging around that's going to give something a negative charge, no matter how you do it. If I shared more, if I took 2 of these electrons and made a double bond there and had 3, that's going to make sulfur a -1. So then we'd have another -1, and then I could do that there again, and then sulfur would become -2. So no matter what, you're going to have at least a formal charge overall of -2. Okay, so Jason, you should either look it up. It'll either tell you in the problem, or it'll say something like, "Hey, it's something sulfate." You look up sulfate and figure it out. Or if I just gave you like a structure like that, you could just count up how many valence electrons there should be, and then find the difference between how many there are. So fine, your question. I got rid of the charge on sulfur because if I have all single bonds, okay, that means every single oxygen is the same, where it has 7 valence electrons. 7 formal electrons, and oxygen only starts with 6. So valence electrons minus formal electrons, 6 minus 7 is going to give -1. So all of these oxygens would be -1, okay? And then sulfur only having just 4 single bonds, that's a count of 4 formal electrons. Sulfur also starting out with 6, like oxygen, they're in the same group. So there, 6 minus 4 would be +2. So with all single bonds, you'd have a +2 charge on sulfur, and all the oxygens would be -1, which would net give you a -2 charge. Okay? But by making double bonds, by expanding sulfur's octet and giving it technically more than 8 valence electrons, but it really only ends up with 6 formal electrons, which is what it wants. So that's why it does that, to neutralize its formal charge. Okay, but you can only do that 2 times, because you got to have at least 2 -1s, and oxygen is going to be more likely to be -1 as opposed to sulfur, because oxygen has a higher electronegativity. It's going to pull on electrons more, so it's going to go -1 versus a sulfur. Hey, Emma, you asked, what is the quantum of energy released from 440 nanometers of blue light? I answered that question last night. So 12:19. It's maybe about halfway through. With that question, you're going to need to turn nanometers into meters. So like when I'm starting the question about a couple minutes in, I'm like, oh, by the way, we need this in meters. So I kind of just say, hey, here's what it is in meters. And then I finish that problem, but then afterwards I show how to turn nanometers into meters, because you need that for that question as well. So if you go back to the last video, if you can't find it, email me and I'll let you know where it's at. But it should be about in the middle. I do that exact problem. Jason said, just to clarify, O2 is oxygen, right? Yes, O2 is oxygen. Okay, those are one of the Brinkelhoffs. O2, Br2, H2, Cl2, I2, F2, and what am I missing? N2. Okay, those are all the Brinkelhoffs. They all, on their own, are just their name, because we breathe in oxygen. We breathe in O2. not just O atoms. Okay, oxygen atoms aren't just hanging out. Normally, no one atom is just hanging out, except for the noble gases because they're stable. Everything else bonds to become stable. These elements commonly bond with themselves to become stable. Nitrogen is a very stable molecule that has a triple bond that it takes a lot of energy to break that bond. So those by themselves are what we call the diatomic elements. They exist in nature as that way. Okay, so we don't say dioxide, we just say oxygen. Okay, we breathe oxygen, not dioxide. Though the most common mistake is people memorize that and then they think, oh, when it's bonded with something, it's going to be two, and that's not true. Like CO2, it's not O2 because of the Brinkelhoff. It's just that's the way that it is when it shares electrons. You can also end up with carbon monoxide, CO. Okay, or you can have like N2O. Okay, here you only have one O. Okay, there you have two. You can also have something like NO2. All of those are totally fine because they're bonded to a bunch of different elements. There's multiple elements there. These have nothing to do with the Brinkelhoffs. They're only when they're by themselves. Okay. So Daniel's got number 43. And then Heinrich, you asked a question, right? I got to get to Heinrich's because it's been a while. Fani, generally, no, you do not want a charge on the central atom. Though, so generally your central atom is going to be more positive than the rest. So just real quick, if I was going to draw ammonia, it's actually this. Sorry, not ammonium, is like that. So there is a charge there, but it's the positive charge because those are all zero formal charge. So there's one instance where you do have a positive or a charge on the central one. Okay, I gotta get to Heinrich. Heinrich said, how do you determine the, oh wait, no, that's not it. Question 11 on the final practice test is to convert 5.3 kilograms per milliliter to grams per liter. How do you do that? Well, let's do that problem. That's probably a more complicated dimensional analysis problem. So we got, can you see that? Yeah, 5.3 kilograms per milliliter. And we want to turn that into grams per liter. Okay, so many grams per liter. Okay, so this is a dimensional analysis problem. We got to turn kilograms into grams. We got to turn milliliters into liters. Okay, so I'm going to have one conversion factor, one fraction that I got multiplied by. That's going to get me from kilograms to grams. I know the relationship between those two directly, so it's just going to be one. And then I got to go from milliliters to liters. I also know that relationship. Both of these are just metric conversions. So I'm going to need a two-step problem here. I'm going to need two conversion factors. Okay, one is going to turn kilograms. It's going to cancel it out and give me grams. Okay, and the other one, I'm going through this kind of quick. And the other one is going to turn milliliters into liters. Milliliters starting on the bottom to begin, so it's got to go on the top. And liters is going to go on the bottom. Okay, so that's what my dimensional analysis is going to look like. Now I just need to fill in the relationships of these units. Okay, so I need to know how many grams are in how many kilograms. I know kilo is bigger than the base unit, so I'm going to say 1 kilogram. Okay, and then if you look at your metric prefixes, you'll see that kilo says 10 to the third. That's the power for kilo, power of 10, 10 to the third. What that means is 10 to the third of the base unit, in this instance just grams, 10 to the third or 1,000 of those is 1 kilogram. Okay, and then milli is similar, and milliliters with the base unit, milli with your base unit is also similar, except milli says 10 to the negative 3. Okay, and that means that's saying 1 milliliter is 10 to the negative 3 of the base unit. Okay, so, you know, what the heck, let's just do that. Here I put 1 as the bigger thing. Here I'm putting 1 as the smaller thing. So that's why this has a negative power, because that's like 0.001, because it's the bigger unit. Here it's 10 to the positive 3, which is 1,000 grams, because that is a smaller unit than kilograms. Metric prefixes are hard. They take practice. So setting this all up here, if I did my math, it would be 5.3 times 10 to the third divided by 10 to the negative third, which is also like times 10 to the third. So we'd actually end up with 5.3 times 10 to the sixth. If I did my mental math correctly, we should end up with 5.3 times 10 to the sixth grams per liter. I wish I could tell who's on here, because I have no idea if, like, Heinrich, if you're still even on here. Okay. Daniel, question 43 on the practice test. You give us the energy of a wave, and we have to say what type of light it is. So do we need to know the wavelengths that each type of light on the spectrum is? No, you do not need to know the range. Okay. That question just throws it in there. You can use resources to answer it. It is not like what will be on the test. On the test, it'll say something like, hey, here's the energy, what's the wavelength? Or here's the wavelength, what's the energy? It might throw in something like, hey, it's blue light, but it's got to tell you some number. It's got to tell you the wavelength, it's got to tell you the energy, it's got to tell you the frequency. It has to give you one of those, because you don't need to memorize those. All right, does anybody have any quick last-minute questions? Otherwise, I have an eye doctor appointment, so I got to get out of here. No, I cannot make the test easier. Sorry. You can make it easier by making sure you know what you're doing. Emma, a lot of what is on the practice test is similar to what will be on your final. It doesn't cover everything. There's some stuff that isn't on your final, but the practice test is to give you an idea of what your final questions will be like. They're not going to be the hardest of problems. Some of them will be hard, but they're generally not going to be the hardest. Some of them will be pretty easy, most basic, but a lot of them are going to be kind of in between. For instance, light calculations. The one that you asked about earlier, that's like a hard light calculation, because I give you nanometers, which you have to convert to meters, and you have to relate energy with wavelength, which means you have to use both equations. So you have to do 2 calculations plus a dimensional analysis conversion. So that one's a hard question. So that could be on your final, but most of the questions are not going to be that in depth. Okay? The final is a summation of everything we've done. Most of the questions are about, moderate. It is a lot of information, though, so that's what makes it hard. You have to remember all these things we've talked about for 4 months, when normally, you cram for a test the night before and then, forget it as soon as you take it. Is there anything not on the practice exam in the final? Jason, I have no idea. There could be. I'm going to say yes. There are probably things that are not in the practice exam that will show up on your final. Okay, so make sure, you can do any question we've had on a test that you don't have the test, you can't do that. But anything we've gone over could be on your final, regardless if it's in the practice test or not. Jesse, if we know everything on the study guide, we'll be fine. You'll be in much better shape than if you didn't. That probably will cover 80-ish%. I'm just making that up. I have no idea if that's actually accurate. Maybe it is 100%. Maybe it's only 70. It's a good representation of what the final will be like. If you really wanted to study a lot, study the practice worksheets we've done. There should be answer keys posted. You don't have to do every problem, but if you go back and do every, practice worksheet, 1 or 2 problems, that'll cover a lot of what would be on it. Okay. Same with study guides. They're kind of like practice tests where they just give you like an average of stuff. Go back in the notes. Everything that we've talked about will for sure be in the notes. So there's nothing on the test that's not in the notes, but also the notes don't have like difficult questions in them because it's giving you the information. The practice worksheets are going to be like assessing if you can do the problems. So I would do notes, worksheets, and the practice final. That's a lot of stuff though. So obviously, use your time wisely. Don't do every single problem we've ever done. That's probably impossible. Yes, a lot of stuff on the advanced chem practice test should be similar to the advanced chem final. It might not cover everything, but a lot of it will be similar. Okay. All right, I'm going to cut it off there. Thanks, guys, for you Gen kids that asked questions. Where's my list? I got Jesse, Emma. I'll give you guys a couple extra credit points for coming on, and I think that was it. Anybody else? If you guys have any dire need of a question being answered, you can email me. I'll try to get back to you. But again, doing a math problem isn't super easy over email. And I'll be here. I'll be at school tomorrow at 7 a.m. so you can catch me then too. Okay. All right. See you guys. Good luck. Don't stress about it too much. You'll be fine.